Hey everyone, in this video, we are going to perform modal analysis on this simple tuning fork. For those of you who don't know, tuning fork is a simple instrument that is used to demonstrate how a vibrating body can produce sound in physics laboratories. So in this video, we can look at what are all the natural frequencies at different modes for this tuning fork. Let's get started. Before we go into the actual simulate environment, we have to assign a material for this part. For that, I'm going to right click on the model here on the model tree, go to edit materials, go to standard ferrous materials. So here I'm going to assign steel low carbon. So when the metal is assigned, you can see the steel low carbon in this materials column here. So the default metal would be PTC system metal properties, but you can just override it and keep steel low carbon. So going to exit out of this. Now I'll go to applications and simulate. As a first step, we're going to arrest the bottom surface in all degrees of freedom. So you can see XYZ translation has been arrested. You don't need to arrest the rotation because rotation has been captured using XYZ for solid bodies. So we don't need to arrest it, especially in rotation. Clicking OK. Now that's all we need to perform our analysis, especially modal analysis. Since it does not require any loads, we can just continue with our displacement constraints and material assignment. That's pretty much it. So we'll go to analysis and studies to file new modal analysis. I'll call it tuning fork natural frequency. So we will look at first four modes, and in the output you can see stress, rotations and reactions. I'll click OK. I'll hit the green flag, or you can go to run and start. Since it's a simple model, the analysis has run pretty quickly. Now we'll view the results. So with the analysis selected, you click on view results tab here. So for the first mode, we're going to look at the displacement animation, see how it looks. So we leave it at deform 10% of the model size, show element edges, animate. We'll see with 12 frames per second. So this is the first classic mode of the tuning fork. So whenever this is struck by a hammer in the laboratories, it will produce a motion something similar to this. So this is our first mode. When this is vibrated at even higher frequencies, you will see the second mode, which you can see here. For that, we just need to hit copy on home tab and select the respective mode. Click OK and show this is the second mode. So when this tuning fork is vibrating at a frequency that is much higher than 321 hertz for the first mode, so we'll get the second mode at 345 hertz. You can copy the same screen and look at the third mode. Copy that. Look at the fourth mode. Yeah, so these are the first four modes we are observing for the tuning force. So as you can see, as the mode progresses into 1, 2, 3, 4, you will see an increase in the frequency. That means that you need more input frequency to see this kind of mode shape in a particular object. So your object is kind of stiff for these modes, so you need to increase your frequency in order to see all the modes in an ascending order. And now we can take a look at the stresses. I'm going to close all. Do not show me this message again. Yes. So you open, double click on your results. So now just expanding the screen. In the drop down, you have to select stress and select any of your modes. So the stress that we are going to see here is not absolute. It is just a normalized stress. So I'm going to deformed. Let's say we don't want percentage. Just scale it to 5 times the actual value. Show element edges. Don't want to animate. So this is our stress plot. So this is an indicator of what the stress distribution looks like when the tuning fork is vibrating at a particular mode or a particular frequency. So when you just copy the screen and go for displacement again, just select deform 5%, animate it to 8 frames per second. So in case if you want to document the first mode results, you can do it side by side. So where you have the mode shape on the right side and stress distribution to respective mode on the left side. And we can take a look at other stresses as well. Just going to close out of this, open. We'll take a look at the stresses for the second mode. This be 5% element edges. So this is our stress. for the second mode. So the first mode and second mode are pretty similar. The one was vibrating side to side and the second one is vibrating back and forth. So this is how you view the stresses. So and apart from stresses, there is one more thing we will see in modal analysis, that is strain energy. Strain energy is an indicator of where your body is strained more, and if your input frequency or your operating frequency just matches with your natural frequency of the body, it will be strained at that spot. And during your structural analysis or structural validation, you should make sure that that zone particularly is strengthened. So let's take a look at that. Let's keep it deformed, show element edges, don't want to animate it. So if you look at the strain energy plot, it is strained where there is rigid constraints or where it is arrested in all degrees of freedom, as well as at the location in this bend radius here. So what we will do, we'll copy this, put a displacement plot just to see where it has deformed. So since this is a side to side mode, let's turn on animate. Since this is a side to side mode, the natural place where it would strain would be this radius here and then at the bottom. So the bottom seems to be strained out because it is a constraint in all degrees of freedom, but in actual case it won't be. So that's one thing. And we can look at, there is a slight increase in the strain energy in this area where your object is tilting left and right. So this area is being strained a little bit. So that is a good indicator of where your object needs to be strengthened. Yeah. So that's pretty much it for this video. So what we have learned here is how to take a particular component, perform modal analysis, and how do we take a look at the results like stress and strain energy. So keep in mind that displacement and strain are not absolute values. You should not take it in a holistic fashion where that's the absolute value. In real case as well, we can take the frequencies close to what it is in reality, but I should not consider stress or strain energy for absolute values. It is a good indicator. We can maybe use it for a comparative analysis between two different designs. So yeah, if you have any questions, please leave them in the comments. So I'll try to answer them. Thanks a lot for watching. Have a great day.